To understand temperature, we have to look smaller than a thermometer. Heat is simply the average kinetic energy of microscopic particles. As they accumulate energy, they move faster and more violently. The universe has a strict rule regarding this energy. It does not tolerate thermal imbalance. It is constantly working to achieve a state of perfect, uniform equilibrium everywhere. To reach that balance, thermal energy is forced to migrate. It always travels from objects with higher temperatures to lower ones, until everything evens out. But heat isn't a fluid you can pour from one container to another. So how does kinetic energy physically cross the space between a hot and cold object? Heat utilizes 3 distinct pathways to travel. The specific route it takes depends entirely on the physical medium it has to pass through. Understanding whether that energy is moving through a solid, flowing through a fluid, or crossing a total vacuum is the only way to predict and ultimately control its path. The first pathway is conduction. This is the primary method of heat transfer within solid materials. When you apply heat to one end of a solid object, the atoms in that specific, localized area rapidly gain kinetic energy. Because particles in a solid are locked in place, they vibrate violently, directly colliding with immediate neighbors. Each collision passes kinetic energy down the line, creating a microscopic chain reaction that spreads thermal energy outward. Metals have loose atomic structures with free-moving electrons that allow these collisions to ripple through quickly, making them excellent conductors. Materials like wood or plastic lack that internal mobility, slowing the transfer to a crawl. Conduction is a strictly localized process. It relies entirely on direct physical contact and atomic density to bridge a temperature gap. The second pathway, convection, operates exclusively in fluids. This includes both liquids and gases, where particles are free to drift and flow. As a fluid is heated, its molecules gain energy and spread further apart. This expansion causes that specific area to become less dense. Because it is less dense, this warmer fluid physically rises above the heavier, cooler fluid surrounding it. As that warm fluid pushes upward, the denser fluid is forced to sink down to fill the empty space left behind. This continuous cycle of rising heat and sinking cold creates a looping pattern known as a convection current. These exact convection currents operate on planetary scales. They drive immense ocean circulation and power global weather systems. Convection transfers heat by physically relocating massive volumes of the medium itself. How does thermal energy transfer when there are no particles available to vibrate or flow? That brings us to the third pathway, radiation. This graph shows the spectral emissive power of objects at various temperatures. It demonstrates that all objects naturally emit thermal radiation in the form of electromagnetic waves, specifically in the infrared spectrum, with total energy emission increasing drastically as they get hotter. Because these are electromagnetic waves, they require no physical medium. They can travel freely through the total vacuum of empty space. When these waves strike a receiving surface, its physical properties dictate what happens next. Dark, dull surfaces absorb radiant heat rapidly, taking in the energy. Conversely, shiny metallic surfaces reflect radiant heat waves away, preventing that energy from being absorbed. Radiation acts as the ultimate thermal equalizer. It projects energy across infinite distances without moving a single atom. In the real world, these 3 pathways rarely operate in isolation. They frequently work simultaneously. This diagram illustrates the combined modes of heat transfer. We see conduction traveling up through the solid metal handle, convection currents circulating within the boiling water, and radiation waves emanating directly from the open flames. Moving from observing these natural laws to actively harnessing them is the foundation of modern engineering. By manipulating radiation and absorption on a massive scale, we can focus thermal energy to harvest clean power from the sun. In the harsh environment of space, where conduction and convection are completely obsolete, managing radiant heat transfer is a literal matter of life and death. Our ability to survive and advance technologically relies on effectively manipulating this invisible, continuous flow of kinetic energy. By mastering the rules of conduction, convection, and radiation, humanity can dictate the inevitable flow of equilibrium. We turn the universe's natural drive for balance into a precise tool for innovation.